in this case, this would be an example where I have, let's say, a simple regression problem. So in this case, I'm using gradient descent algorithm, so which is basically looking at calculating the gradient of the loss function. So the loss function is that weird unknown curve. And so what I have there then is you have the y-actual and the y value. So imagine that if I calculate the mean standard error, that might be the first, like that would be kind of that would effectively be the mean standard error based on that particular iteration. So what I'm trying to do then is once I have the so the MSE in this case is the distance between, as we talked about, is the distance between the expected and the actual value. What I'm trying to do is understand. So imagine if you want to determine so if you have an equation y equals ax plus b. So you want to figure out gradient descent to get the optimal values of a or b. So what you do is you start off with some random guess for what a and b are. And then what you want to do is you want to see how much does the mean standard error change as I change my value of a and b. So if I'm getting close to the right answer, as I fluctuate a and b by a small amount, then I should see that my mean standard error shouldn't change at all. If in an ideal scenario, it'll equal 0. If my model changes, if you see a very high value, that means my value of a is far away from a minimum. So what you're trying to do is ultimately minimize the MSE, which is the distance between the actual output and the expected output. So suppose, for example, I have the MSE, and I have some parameter that I'm varying, let's say a. Then what will happen is that with different values of a, I could get a curve like this, right? So what that basically means that as I fluctuate a, I get different error outputs. So the reality is that it's multiple dimensions. I'm just showing you one dimension, pretending that it's just one value. So as I move along this curve, if I end up here, based on the backpropagation algorithm, I'm stuck there. It means that that is a minimum, but clearly that's not the best answer because the best answer is down there. That'll give me an even lower MSE. So the backpropagation algorithm will give you a minima for the MSE. So the whole point of machine learning is to figure out how do you minimize the error in the system. And how you minimize the error is to actually figure out the derivative. And since there is no analytic way to determine what the derivative is, you use an algorithmic way, which all it does is basically figures out a value of a, calculates some small delta A, and then looks at the corresponding value of y. And if you see a very different, a huge difference between the two values, then you move that to a different point, different a, and so on and so on. So one of the things I'm going to be using polynomials for a lot of these things, just because there is a very tight relationship between the use of polynomials and and actual like determining models for real objects. So because this is a regression model, and so this is a bit about determining the values in this system. So the way you can kind of imagine it is that these themselves are associated with, in quotation marks, weights. These are the actual, if it converges, this will eventually converge to a certain number and won't move from there. So what we're trying to do, so the outcome of a training or model is a model or a predictor. So that M, when it converges finally, is called a predictor or a model. And it can either be very simple or very complex based on the kind of problem. So this goes all the way back to think about feature engineering. If I have a very, very complex model, I'm adding lots of features to it, and therefore my neural network is very big. So it can be a lot of weights. So you're basically increasing the size of the weights, but you may also end up increasing the number of layers as well. So as you start to get more complex. But now if we, let's say, simplify that, so as every time you add a new feature, what happens is you're essentially increasing the number of weights in your system, and then you may also be increasing the number of layers in your system as well. So the higher the number of features you have, that impacts directly the number of weights and number of layers that you need to use in order to build a model around this. So basically in this case, simplicity is just really, so this is a polynomial case. So you have a bunch of points over here. These are the little blue dots. And you want to build a model that roughly approximates, so what is the equation for these blue dots? And so you can pick a very simple model, which is a linear curve, so which is simply a straight line. You can pick a very complex, or you can pick a more complex one. In this case, it is a curve, roughly a parabola. And then you can pick a very complex model, which is a seventh order polynomial. And so that basically gives you this really complex shape. So as you start to build, so each of those are models that you can construct. And the way to think about it is every time I put another x in there, I'm essentially adding another feature. So every time I add a new feature, that makes my model a little bit more complex. So as you add more, so you'll remember earlier we talked about feature engineering. If you have too many features, what could happen is you'll end up in a situation like this, where you have a really complex curve trying to get to these points. If you have too few features, then you could end up with a linear curve. But if you have the right number of features, then you end up with a parabola. And in this case, the parabola is the shape that most closely approximates reality. Right? So feature engineering basically determines how you want to basically get to a point where it's not too complex, your model, and it's not too simple. And if it's at the right level of complexity, then you will be able to minimize the error. And I'll talk about overfitting in a moment to kind of like explain the point. But there are different levels of complexity based on the type of features you picked. So that has a direct correlation to neural networks. So very complex neural networks are very deep and have a lot of weights, and a lot of weights correspond to a lot of features. And when you think about it, in this case, I just have two features. Imagine if I have several hundred features, then in order for me to build a neural network that can describe those several hundred features, I need a very, very big neural network to do that. So one of the challenges, so this is kind of like it's called a bias and variance trade-off. So there are two elements that you care about. Well, there are many elements, but the two key elements you care about in your model. One is called bias, and that's essentially the statistical bias is the difference between what the model predicts and the actual training data. And the variance is the amount it's whether your model picks up noise or whether it actually is picking up it's really learning something. So it's possible that when your AI model is just learning noise because it's basically too complicated, so it literally just learns like variance in your system, that's not good because it has no predictive value. So the challenge is you want to, the ideal scenario is you would like to make sure that there's really low bias and also really low variance. That would be the ideal situation. So simple models tend to have very high bias because they differ from the training data by a very large amount. But they don't capture noise in the system because they don't capture random variances. Complex models tend to have very low bias, which means that they model the training data extremely well, but they capture a lot of noise. So the difference, and then the ideal scenario is where it models the training data very well, but it doesn't learn the noise. It learns to ignore the noise, in fact. So it's actually discovering a pattern. So this is kind of where we want our models to go. And this is kind of, and when you don't go into that, you can either get underfitting or overfitting, which we'll talk about it shortly. Okay, so I'm going to talk about a couple. So basically, these are some of the gradient descent approaches that you use. Stochastic gradient descent is also called online training. And what that basically means is that every time you have a sample, it updates the weight. It updates the weights in the system. Batch gradient descent means that you update weights on all of the data at the same time. And then you've got mini batch, which is basically you break your training data into small batches, and then you update the weights based on that specific batch of data, right? So the best way to see this is visually. I'm a visual guy. So batch training is you have a whole bunch of values. You calculate the deltas from the actual value, and then you, based on the deltas that you calculate, you do back propagation through the system. That's where, in this case, what you're doing is you're as you start to train, and you're basically looking at all of the data, calculating the deltas, and then using the collective set of deltas to go and back propagate. Stochastic gradient, so the standard gradient is you keep putting one data item, you submit row 1, determine the gradient, back propagate, then the next one you go through, back propagate, and so on and so on. And the last one is where I form, so it's very similar to the batch, but yeah, it's basically just breaking up into small groups, calculating the delta and going back. So this is what you typically do, and this is the best training method. So when you set the batch value, the batch size, this is what you're doing. You're setting like how I'm going, kind of grouping the values together. It'll calculate the deltas and then do the back propagation. So mathematically, if you guys are interested in looking at this, this is sort of what happens. So the network parameters here are represented by an abstract value theta. These could be the weights in the system. It could be the value of the coefficients in the equation. So for every epoch, you have a value theta, and you have your input value is x and your output value is y. And so what you're going to do is you'll adjust. You take essentially all of your data. This is gradient vector that represents, that depends on all of the input and output vectors. And the way that's calculated, this could be how it's done. So you take the sum, you take all of your outputs, all of the expected outputs, and all of the real outputs, and calculate the average, and that gives you the delta for that particular, for batch training. So stochastic gradient descent is you don't do the average, you just look at every single value. So every time you calculate the delta J based on the thetas, you just do a 1 you calculate it one at a time, and then you do this. So this is obviously going to be very time consuming because you're going through every single one by one. And then this is kind of what mini batch looks like. So in mini batch, you have your input, same thing, and what you do is you describe it into, divide it into sort of m distinct sets. So you have, this is your like first group of inputs, second group of inputs, and so on up to m. And then what you're going to do is that for every batch, so every one of these different inputs, you will actually then determine the average within that and then back propagate. So it's just very similar to this method, but instead of here I'm taking all of the outputs, and in this case what I'm doing is I'm just dividing the outputs into smaller groups and then taking, like doing back propagation based on that small group.